This video is a reminder of derivatives, and remember that derivatives are only defined for functions of one variable. Okay, so let's look at our function g. Let's say we have a function and we call this function g, and this function is a function of only one variable, so we can represent it here. That variable could be x, usually that would represent a spatial position, or it could be time, but here I'm going to assume that we take as our variable x. And so here is my function. And so at every given spatial coordinate, so at every single location, let's call that x0. If we know the function, we know what this value here is. This is g of x0. So when we know the function, we know the value of the function. Now, what is true in physics, but is true in many other disciplines, is that the value of a function is oftentimes not really what you're interested in, and mostly what you're interested in is how the value of the function changes. So if you think about economics, for instance, you don't necessarily know on the top of your head what the GDP is of a given country, and what interests you most is the growth rate. So how does the GDP changes with time? So this is an example that sometimes you're more interested in how the function changes than the value of the function itself. It's also true in physics. If you think about the laws of physics, oftentimes you know something not about the value of the function itself, but you know something about how that function changes. For example, Newton's second law is not a law where you have an equation for the velocity. It's an equation where you have it's a law for which you know how the velocity changes as a result of a force, for instance. And that information is contained within the derivative. So if I'm at this point here, I may, for instance, wonder, well, if I take a step along the x-axis, by how much will my function increase? This information is part of the derivative, and the derivative, as you've seen before, is really the value of the slope of a line which is tangent to your function. So the slope of this tangent is what we call the derivative, which we call sometimes g prime at x0, or you can also write it straight d dg dx at x equals x0. So you can, the way I would refer it sometimes too is you can think about this derivative g prime or dg dx as being the rate of change of g with respect to another way of writing that is to say that g prime gives us information about how the function g changes with a change in the value of the coordinate x. And often I will denote a change of value of g as a delta g, the change of g, and how this relates to a change of the value in x, which I will call oftentimes a delta x. So this, the definition of the derivative is central to the linear approximation. So what is the linear approximation? Well, let's take our function g again. And here it is quite clear that my function g is a nonlinear function, so it's not a straight line around x0. But at the same time, you see that if you were really to zoom in very closely to x0, so if I was to zoom in close to here, so that would be here my point x0 gx0, and the value of my function, the function g, would look like this. So when you zoom in, this wouldn't be exactly a straight line. There is a little curvature here, but if you're zooming really closely, it looks very much like a straight line, and that is the linear approximation. So here, the linear approximation will be this straight line here. And when you do a linear approximation, then you assume that the value of your function is really close to the value of this linear function, because this distance between the real value of the function and the linear approximation is very small. And so what you know is that if from x0, if you start from x0 and you move a small delta x around x0, then you can very well approximate the value of your function as the value of this linear approximation. And the value of this linear approximation you get from a Taylor expansion, from which you know that the value g at a point in the neighborhood of your point x0, right? So the value, if I move here by a small delta x, so here I'm at x0 plus delta x. So the value of my function at an x0 plus delta x, so here is this point, and the value is equal to j at x0 plus delta x. So j at x0 plus delta x is equal to the value at x0 plus the value of the derivative of g at x0, so it's the value of this slope here, times delta x, plus, of course, this little piece here which we neglected, which scales with delta x squared, so it's very small if delta x is small, and we call these higher order terms. So higher order terms. And the linear approximation is simply to say that we neglect these higher order terms here, and to directly say that this value, so the value of the function in the neighborhood of x0, is roughly equal to this, which is the value you would get by assuming that you had a straight line, so this blue line here. So g at x0 plus delta x is roughly equal to g at x0 plus the value of the derivative at x0 times delta x. And from here you can clearly see what we discussed before about how can we interpret the value of the derivative of g. So if you ask yourself how does a change in x change the value of the function g, so change the value of g, which is the same question as asking what is the change of g, what is the change delta g of the value of g when x changes by delta x. Well, then you can directly see here that this delta g is equal to the value of the function at x plus delta x minus g x0. So delta g is just equal to the derivative of g at x equals x0 times delta x. So the value of the derivative is what relates a change in x to the change in delta g. So if you want to know how does delta g changes when you change x by a certain delta x, then you just look at the value of the derivative. This is also linked to the concept of total differential. So the differential of the function g, which you call dg, is equal to dg dx, so the derivative times the differential of x.